first speaker is Dr. Locke Karriker. He is the director of the Swine Medicine Education Center at the Veterinary School at Iowa State. He has a presentation on the best practices for ractopamine elimination. Please welcome him.
I hope you can gather one. Before Locke gets started, does everybody have a ticket for the raffle drawing? Or does anybody need that? Okay.
All right, good to go. Raffle tickets are probably more important than ractopamine, at least in the short term. So thanks for the opportunity to speak with you today. I appreciate everyone coming out. As I go along, if you have questions, just feel free to shout those out. Don't even bother raising your hand, and we'll try to address those as I can as we go through this. So a little bit of background about what's become the ractopamine issues of late. So in order to gain and preserve access to some international markets, many countries have actually banned ractopamine. Actually, over 100 countries have banned ractopamine. And so in order to preserve or gain additional export market access, several processors in the U.S. have announced their intention to only take ractopamine-free pigs as part of their processing. And so that creates a bit of an issue with respect to how are we going to test for that and how are we going to monitor that and so forth. It's important to note, though, that there haven't been any recent changes in the regulatory status of ractopamine. This is not a food safety or a health issue. It's a political difference really among countries with respect to what's banned in some countries and legal in others. And I'll talk you through that in just a little bit. So we want to make sure that up front we're pretty clear about the fact that this is not a food safety or a health issue. So what is ractopamine? What does it do? How long do the effects last? I think those are important background pieces of information. And so what you see with this particular graphic is ractopamine is a beta agonist, which is a broad category of drugs. And those drugs generally stimulate these beta receptors, beta agonist receptors. And those receptors exist on many tissues, almost all the tissues throughout the pig's body. And they all have slightly different functions depending on what cell they're in and exactly how many of them there are in that particular cell or organ. But once a beta agonist, and there's a broad class of these, once it binds the receptor, then it starts a cascade of conversions that ultimately ends up with this enzyme phosphorylation step. And that basically takes some proenzymes and activates those enzymes. And when it does that, in muscle cells and fat cells, it has some particular effects that are important to lean growth accretion in the pig. So in fat cells, you basically get a decrease in fat synthesis, and you get an increase in fat breakdown. So the net effect is that cell stores less fat, okay? In the muscle cell, what you get is an increase in protein synthesis and protein deposition, and a decrease in protein breakdown, okay? So a couple of the nuances about this are important when we start to think about removing it and or substituting for ractopamine or managing it. So for example, these changes are not permanent changes, okay? We're not changing the number of fat cells, we're not changing the number of muscle cells. So we're changing the content of those cells. And when you remove the beta agonist, then these processes start to go back to what they were as baseline for that particular pig. So over a period of time, the pig will return to what its baseline carcass composition was in terms of fat and lean. It doesn't happen immediately, but it starts to happen as soon as you remove the beta agonist. So there are no permanent changes necessarily associated with this. There's also a limit to efficacy if you feed the beta agonist for longer. There's a period of time where the pig becomes less receptive to the effects, and they start to down-regulate these receptors. And so there's sort of a sweet spot in terms of how long you feed it, and that's why it's labeled as it is. Okay, so what's the difference between the U.S. Food and Drug Administration tolerance level and being completely free of ractopamine? And this will sound like a little bit of sort of nuanced technical jargon stuff, but this gap is really what we're faced with when trying to eliminate ractopamine from systems, and it's a bigger gap than you might imagine. But let's first look at how the FDA established their tolerance level for us to, in order to use it. So you can actually find all the information that the FDA used to approve the drug, and any drug for that matter. If you go to the FDA website, you can search these Freedom of Information Act drug summaries, and you can put ractopamine in this particular spot, for example. And what you'll get is a document that has a lot of bullet points like this. In this case, I think it's about 48 pages long. A lot of details about how they approved the drug and established a tolerance. All the studies that were used to confirm its safety and to establish how we use it are contained in that document. So you can read that, and it's rather transparent. I'm going to walk you through the steps that they use to confirm that to establish a safe level and establish essentially a zero withdrawal period for ractopamine. So the way they started is they found the no observed effect level in the closest species to humans for the physiological system targeted by the drug. Okay, and this is a process they use for all drugs. In this particular case with ractopamine, they had a lot of studies. There was a time in the distant past where ractopamine was investigated for use in the military. There was, it was looked at as a potential drug in humans, and so there was a lot of study work, and they actually had studies both in monkeys and humans directly. And in these studies, the organisms are given the drug directly. It's not diluted with pork. So the highest no observed effect dose, in this case, one where monkeys were administered ractopamine daily for a year. So they actually got injected with ractopamine every day for a year. And if you've ever worked with monkeys, they're almost less fun to inject than sows. So somebody paid yearly here. But anyway, they treated them once daily for a year. And that dose was 0.125 milligrams per kilogram of body weight every day. Okay. Now, later on, we're going to talk about parts per million and parts per billion and even parts per trillion. So mgs per kilogram are parts per million. And the relevance of that will be apparent here in just a few slides. But to continue the process, they then determined the acceptable daily intake. And to do that, they apply a safety factor of 100 to the no observed effect level, so that that acceptable daily intake then becomes 0.00125 milligrams per kilogram per day. So it's just a arbitrary safety factor. Then that acceptable daily intake is multiplied by average body weight. Okay, so they use 60 kilograms. If you're above 60 kilograms, you have a little extra safety, right? So grab another pork stick there in the back. It's another reason to finish dessert. They then divide that by a food factor, which is how much of the target pork tissue that is typically consumed in a day, to determine the safe concentration in edible pork. Okay, so several steps here to get to this point. And then what they do is they feed pigs a radio-labeled version of the ractopamine. So they actually label every molecule of the ractopamine, feed the pigs. They can follow every single molecule, so anything that gets metabolized, gets excreted, gets retained in the animal, all of that can be tracked as part of those radio-labeled studies. And they look to see how much is excreted and how much remains in tissue, and then they establish a withdrawal period that puts those residue levels in tissue below the safe concentration level that we just calculated, okay? In the case of ractopamine, the minute the pig quits eating it, they're below those safe concentration levels in tissue. So at that point, the pork is safe for people to eat based on their past studies and the safety factors that we put in. Okay, so here's a summary of the studies that were used to determine the tissue levels. So on the left-hand side here, we have the tissue, we have liver, kidney, muscle, fat. This is a safe tissue concentration we just calculated. And you'll notice it's a little different for each tissue, and that's a reflection of how much of that tissue the FDA thinks you'll eat. So we generally eat a lot less kidney than we do, say, muscle or loin. And so that hence the different concentration levels. And then these are 4 studies where they radio-labeled the drug and then looked to see what the highest concentration was that remained in the animal. And you'll see of all these data points, the highest was 0.6, which is below 1.5 parts per million, which we had established as a safe concentration. All right, 0.6 is also 600 parts per billion and 600,000 parts per trillion. And this becomes important because 30 parts per trillion is the lowest reported detection level. Ractopamine is a drug that's been used for years. It's a relatively easy molecule to detect with a lot of the chemistry that we have available. And so ractopamine is something that we have very, very sensitive testing for, and that's a bit of a hurdle for us as we remove it. So if a pig is directly fed ractopamine according to the label, it's potentially going to be detected for extended periods, right? We got to have enough time elapsed to go from that 6.6 parts per million all the way down to 30 parts per trillion. So it's a big difference in concentration. And there is no extra label use of ractopamine or ractopamine products in the feed. So you really don't have leeway to feed it, establish a long withdrawal time, and then subsequently market the animal and hope it'll test negative. You also would lose the effect of the ractopamine anyway, so there's not a lot of economic incentive to do that. So there's essentially no mechanism to feed it and test negative via extended withdrawal. And it would probably be easier if that's where the story ended, but what we really worry about is, are there situations where we're going to need to test and confirm, and are there risks for contamination? So this is a question I get periodically. Is there a test which would allow checking pigs at a county fair, for example, with results before the pigs are shipped? And the answer is yes, we have tests. There's a big but on the end of that. There are a variety of validated tests, actually. So we have liquid chromatography, mass spectrometry tests, so gas chromatography, mass spectrometry tests. These are lab-based tests. They're conducted on a workbench in a laboratory. They're basically the ractopamine is separated from whatever sample you're using, and then it's blasted with energy, and we look at the parts and when they fly apart, and that's how we determine what's there. Then we have lateral flow devices. So this is much like a pin side test. It's sort of like a pin side, dog side rabies test that you might have seen, or a heartworm test or a pregnancy test. And so they're small snap devices in a lot of cases. And then we have ELISA test, which is the exact same technology that we use to look for antibodies. So you might have seen an ELISA test for a disease, for example. Both those lateral flow devices and the ELISA test can be deployed in the field at pin side almost real time. There's not a lot of sample prep associated with those. The other two, the gas and the liquid chromatography or laboratory-based tests, they take a little more effort to prep the samples and that sort of thing. But in total, there's 11 tests that are validated, and the lower limit of detection ranges from 250 parts per billion to 0.25 parts per billion, and they've been validated in feed, urine, tissue, and plasma. So we have a wide range of testing options. They're very sensitive. These testing options range in cost from $250 to $675 per sample. So you get a visit with your diagnostic lab and or your veterinarian potentially, and make sure that you're getting the best value out of that testing expense, if you choose to do that. So I mentioned earlier that at least in research studies, tests as sensitive as 30 parts per trillion have been reported. We think in our lab we can probably get it down to single digits per trillion. So again, easy to detect at very low levels. Now, how do we get our head around what a part per trillion is, right? Because really understanding that's going to help you understand what you have to do to eliminate it from a system, eliminate it from farms, and so forth. So it's a big number. It's really hard for me to get my head around. So I'm going to give you an example. So this is a 1-inch cube. It's a little granite piece of rock here. It's actually a whiskey rock, right? If you're familiar with those, so you freeze it, put it in your drink of choice. Doesn't dilute it with ice. I'm not marketing it, but that's what it is. So it's about a 1-inch cube, right? This is going to be our part. This is the part that we're going to look for in a bigger pile, all right? So how big would the pile be if this was 1 in a million or 1 in a billion or 1 in a trillion? How big a pile would we be looking for this and be able to find this in? So most of you familiar with Iowa State's campus, hopefully you've been up there to tailgate or something fun, or maybe go to the D-Lab, something not so fun. But here's basically a map of most of the campus. Here's where the campanile sits, right on the main quad, and then here's the athletic complex, Jack Trice Stadium here. Here's Hilton Coliseum, and then this is the parking lot where the best tailgating happens. And you can barely see the line of tents here right down the middle. I think this was taken early on. So the campanile is 110 feet tall, slightly taller than the tallest part of the football stadium, or it's 1,320 of these whiskey rocks tall, okay? So how big an area would we have to cover if we stacked rocks to the height of the campanile? We're going to zoom in, We're going to go to the stadium. Now we're at midfield in the stadium. And if we wanted to create a stack of 1 million rocks, we would basically have to stack them as tall as a campanile, and they would cover a little under a square yard right here at midfield, okay? So there'd be one of these in that stack, and that would be a sensitivity of 1 part per million, all right? Now, if we wanted to look at 1 part per billion, we got to zoom out a little bit, and now we're at midfield, and we're going to cover almost the entire emblem here at midfield. This is a square that's about 27 yards square, give or take, and it's as tall as the campanile. And if we can detect 1 part per billion, we can find this rock in that pile, okay? If we want to talk about 1 part per trillion, then our pile of rocks has to be as tall as a campanile, and it covers Jack Trice Stadium, for the most part, all of the tailgate parking lot and Hilton Coliseum from road to road. It covers that entire space, and it's as tall as the campanile. So if you're able to detect something at 30 parts per trillion, you can find 30 of these rocks in a pile as tall as a campanile that covers everything from Hilton to at least the high rent district there in Jack Trice Stadium. So very, very sensitive test, finding very small pieces in a big pile. So as you can imagine, contamination via a variety of potential routes is a real problem. It doesn't take much of it. It can be carried potentially on dust and things like that, and ultimately be found in some of these tests. And we've seen some issues with that. So this is a little difficult to read here on the side, and it's even worse on your handout, but it's on the Iowa Pork Industry website on the ractopamine frequently asked questions page that's linked there, so you can find it in a form that's a little easier to read. But it's a checklist that Dr. Rademacher had a hand in putting together to sort of figure out questions you might need to ask to try to clean your system up if you're going to go ractopamine free and you want to avoid these contamination issues. So, first of all, have you knowingly fed ractopamine, in which case you got to find a market that will accept that. If you haven't, then you've got to ask if you fed pigs from a mill where other pig or cattle feed was milled at the same time, because those other species use ractopamine products. Other producers might still be using it in their pigs. So you want to know about that status. Can you verify the mill has never fed ractopamine or has ceased feeding it and has cleaned the mill before the pigs consume feed from that mill? That's probably going to be necessary to have confidence that you remain negative. Can you verify that all the feed ingredients in the swine diets are free of ractopamine? So there are some things that are used in parts of our industry that have ractopamine that may not be that obvious. So you want to make sure you know everything that you're feeding to the pigs directly in terms of supplements and top dress and things of that nature. You want to know if you can verify whether bovine meat and bone meal, beef tallow, or blood meal is being used in the same facility that you're free from cattle use ractopamine products. And so there are several opportunities there potentially for cross-contamination. It stays in these tissues. It's not exactly broken down very well by the processing of those tissues, so could potentially show up that way. Have you cleaned the on-farm feed bins and so forth that have used ractopamine feed in the past, right? Everybody's seen a feed bin that's been in service for a couple of years. There's some buildup of dust and feed inside. You have to think about transportation. You're probably going to only want to use washed transportation trailers to take the pigs to market. Make sure that they haven't been exposed to the urine or feces of other pigs or other animals. And you want to make sure they haven't been exposed to the feces or hair of other pigs that are of unknown ractopamine status. We know we can detect ractopamine in hair for up to 42 days after the pigs have consumed it. So that's another depot potentially for exposure. And if those pigs are exposed to that, go into a plant where the testing process is using oral fluids, for example, then there's a fairly direct mechanism for carrying that doesn't reflect a pig's status. Do you have testing results from representative samples? I think at least that's not something you're probably going to do on an ongoing routine basis, but at least initially after you eliminate it, you're going to want to do some testing to confirm that you've got the system clean and free. So some things to consider there in terms of the steps of the process. Get this question a good bit. Can we differentiate between a pig that's fed ractopamine directly and one that's been contaminated by one of these routes? I think that'll be important to people. And unfortunately, it's an ambiguous answer, not yet. And here's why. So let's imagine that this is a pig that's actually fed ractopamine directly. So they have a high concentration after it's been fed to them, and then of course that gets excreted and metabolized and disappears, and down here at this end they're finally negative or free of it. And then you have a pig that's potentially been contaminated. They don't have as high of initial, as high of an initial exposure, but then that's going to decline and wane, and eventually they'll be free down here. So when you think about this time frame, we can probably, with a little bit of research to define the levels, we can probably distinguish the difference between these two pigs based on quantifying how much ractopamine's in the sample. But even with additional research and additional test options, these are always going to look the same. So at the very tail end, when pigs are finally getting rid of it, it's going to be hard to know whether they were fed it directly or whether they got it through some route of contamination. So that's going to continue to be problematic. What are the alternatives to ractopamine? We're going to pull it out. It's obviously valuable from a composition standpoint. So what are the things we can do? Some of them are sort of hard answers, right? Prevention, increased biosecurity, do what we already know works. It makes your biosecurity and prevention of disease all the more valuable, since you need to make sure pigs aren't diverting energy to other things. Reconsider things that alter the gut biome, such as mass medication, all right? Let's make sure that the antibiotics we're using are necessary, that they're timed in a manner that actually impacts bacteria that are pathogenic. Give you one example. If you give a day-old pig an injection of penicillin, it changes the distribution of bugs in their gut for 5 weeks. So that changes their ability to metabolize and use nutrients and so forth. So those mass medications are not without some downside. You got to make sure that the upside or the value outweighs that. Immunocastration, maybe it's time to reconsider that a little bit in terms of raising boars is certainly another way to change your gain profile. Reconsider and revise vaccination programs, right? If there's no exposure to the pathogen, then vaccine programs are really all cost. If they never get exposed, they never use that immunity, then they've spent time and energy developing antibodies, and they've repartitioned energy to develop an immune response to prepare. If they're never challenged and never use it, that's wasted energy, right? We can't sell the antibodies. So make sure your vaccine programs are current, they're up to date. Make sure you have some reason to believe that the threats are out there. Manage the environment correctly. This is where we see a lot of energy leave the pig, and there's a lot of waste. If you can smell ammonia, if the pigs are piling, and get those things fixed, because that's energy that's going out of the pig pretty rapidly, right? And I'll give you an example on the ammonia. Ammonia is very effective at paralyzing one of the innate defenses of the lungs. So ammonia will actually paralyze the little cilia that line the trachea and filter out bacteria and other pathogens and problems. If you get rid of the second innate defense system of the lungs, which is circulating macrophages, and PRRS virus manages to do that, by the way, then the lungs are wide open to bacterial secondary problems that will make the pig sick and divert energy for response. So try to stack the odds in your favor and take care of the things that you can impact or alter. Investigate water quality. This is something fairly new for me in terms of understanding, but there are parts of Iowa where you can smell hydrogen sulfide, or the water has a distinct smell. You usually notice it when you're showering in, for example. And it's important to remember that a lot of the natural sources of sulfur are actually sulfates or sulfites, and they've got to be metabolized by something to get to hydrogen sulfide. And usually that means there's a bacterial presence somewhere in the water line or somewhere in the system. It's just probably a good indicator that you might want to think about cleaning that system out, or see, and at least investigate and see what the risk is there. And then involve a skilled nutritionist, right? We'll have one on the program here later today. So since he's not here to defend himself, we'll just save all questions for him when he comes in later. But those are the things that I have prepared. I'm happy to entertain any questions that you have. Yes, sir.
If the feed dealership is grinding cattle show feed with Optiplex?
Optiplex or Optiflex. Yep, okay. That's right.
And they're grinding that, and then they turn around and grind 18 ton of hog feed. that in that whole feed?
I mean, I think there's a risk that there is, and I think the questions that you want to ask are, first of all, is your feed mill doing that? So does that risk exist? And then what steps are they taking in between to put barriers to cross contamination? How are they handling dust and dust containment? You know, feed mills are really difficult to clean because you don't want to put water in a lot of the moving parts. So we tend to clean them with compressed air, and that's something that you're probably going to have to do multiple times in order to run all of that dust out of the system. But I think that's a legitimate risk, and I think that's something that you have to have a dialogue with them about how they're going to manage that.
Will they get salts of Optiflex in the swine?
So the active ingredient in the Optiflex is the same as it is in the swine product. So yes, it'll show up on the test as if it were the swine products, and there's no way to distinguish which is which on the testing level that I'm aware of. But yes, sir.
What's a realistic timeline to be able to get a female clean?
I mean, that's a really good question, and I would struggle to give you an honest answer about that because every feed mill I've been is a little bit different, laid out a little differently, and some are older, some are newer, some are easy to clean. You know, we have anecdotal stories of it taking a couple of months because not so much because ractopamine is hard to clean up, but because they have to find the nooks and crannies that are still potential risks to the process. So it's more of that issue. Ractopamine's water soluble. It's not terribly difficult to get rid of. So it's not something that's going to be hard to get off surfaces or things like that. It's just a matter of finding all the possible cross-contamination points and places where dust still exists and falls into feed and things like that. So sorry, that's not a very good answer, but that's honest as I can be about that. It's not going to be something you're going to shut down for a weekend and drop the hammer on and be good to go on Monday, though. I think you're going to clean and test and clean and test.